This is your presenter Asloob Mudassar, and I am presenting slide number 57 of the course on laser physics. Question is, derive expressions for transition cross sections, gain and absorption coefficients for the case of strongly coupled sublevels. The answer is, in a two-level system, level 1 and level 2 consists of G1 and G2 sublevels with different energies but with very rapid relaxation among sublevels. That is, the sublevels are strongly coupled. Some of the sublevels in level 1 and level 2 may be degenerate levels. Boltzmann's statistics will be obeyed if quick thermalization among the sublevels exists. We can write N1I is equal to F1I N1 as in equation number 1, and N2J is equal to F2J into N2. N1 is actually the total population of level 1. N2 is actually the total population of level 2. N1I stands for the ith sublevel. So N1I is the population of the ith sublevel from level 1. N2J is actually the jth level of jth sublevel of level 2. So N2J is actually the population in the jth sublevel of level 2. F1I is the population of the sublevel. This is F1I is the population of the sublevel divided by the total population of level 1, and similarly F2J is the population of the sublevel J divided by the total population of level 2. So all the terms have been explained in equation number 1 and 2. So let's read next, where F1I is the population of sublevel I divided by the total population of level 1 under thermal equilibrium, and F2J is the population of sublevel J divided by the total population of level 2 under thermal equilibrium. Thus we can write that F1I is equal to G1I into e to the power minus E1I over kT as in the numerator. This is actually the population of the level of the sublevel I. So this is in the numerator we have G1I into e to the power minus E1I over kT. This is the population of sublevel I. So and divided by in the denominator we have the total population of sublevel 1. Total population of the level 1, which is summation over L, from L is equal to 1 to G1. G1 is the number of levels, number of sublevels present in level 1, level 1. So we are summing from L is equal to 1 to G1, and you see that we have the same terms as in the numerator, that is G1L into e to the power minus E1L over kT. So the numerator contains the population of the sublevel I, and the denominator contains the population of all the sublevels summed up together, that is the population of level 1. And similarly we can write F2J is equal to G2J into e to the power minus E2J over kT, where G2 is the number of sublevels present in level 2, and we have the numerator is actually the population of the level of the jth level in level number 2, and the denominator is m is summation over m is equal to 1 to G2M into e to the power minus E2M over kT, and m you see that is the mth level, which is being mth level of the level 2, mth sublevel of the level 2. So we are summing up all the populations of the level of the sublevel m, because we are summing the level m from 1 to all number of levels which are G2. G2 are the total number of levels present in the level 2. So summing over all the sublevels, this becomes the population of all the sublevels summed up together in level number 2, or actually the total population present in level number 2. So we have written F1I and F2J, and we have also explained all the terms within these. where E1L is the energy of the nth sublevel of level 1 and E2M is the energy of the mth sublevel of level 2 with respect to degeneracies G1L and G2M. Consider transitions, both absorption and emission. You know that when we are talking about the emission, we have two types of emissions: stimulated emission and spontaneous emission. But when we are talking about absorption, we may simply call it as absorption or stimulated absorption. So consider the transitions, that is the absorption and emission between two sublevels L and M of level 1 and level 2 respectively. The rate of decay of population of the upper level dN2 over dt, including stimulated emission, absorption and spontaneous emission, is given by, so we have dN2 over dt is equal to minus WML multiplied by N2M. This term corresponds to stimulated emission. Then in the blue we have WLM multiplied by N1L. This is the you see that there is a positive sign with it, and this is the absorption term. And then we have in red, we have two summations: I is equal to 1 to G1, J is equal to 1 to G2. That is I stands for all the sublevels in level number 1, and J subscript stands for all the levels in level number 2. The total number of levels in level number 1 are G1, and the total number of sublevels in level number 2 are G2. So summing up over all the sublevels in the level number 1 and level number 2, and then we have N2J over iota Ji. N2J is actually the population of the jth level from level number 2. And tau Ig is actually 1 over tau Ji becomes actually the spontaneous rate from the jth level to the ith level. So 1 over tau is actually the spontaneous rate emission, the spontaneous rate. So 1 over tau Ji is the spontaneous rate from the sublevel J to the sublevel I. So let's go back to the green term, which is due to the stimulated emission, which is minus WML. So minus WML means that the transition, this is the transition rate from the sublevel M of level 2 to the sublevel L of level 1. And then we have N2M. N2M is actually, M stands for the sublevel, small m is actually the sublevel, mth sublevel of level 2. So N2M is actually the population of the population present in the sublevel M of level number 2. And similarly, let's come back to let's go to the blue term, which is WLM. This will give you the absorption rate from the level L to the level M, and you know that level L is the sublevel of level 1 and M is the sublevel present in level number 2. So WLM is actually the transition rate, that is actually the absorption rate from level L, sublevel L of level 1 to the sublevel M of level 2. And you know that N1L is actually the population present in the sublevel L of level 1. And you see that the other terms have been explained. So that's why you see that we have a negative sign with the two terms, with the green terms, which is the emission term, which is the stimulated emission term, and the red term, there is also a negative sign because this corresponds to the spontaneous emission term. So you see that due to these two negative terms, the population of N2 will decrease, and due to the blue term, which is the absorption term, the population will increase because there is a positive sign over here. So I think that all the terms in equation number 57.3 are explained. Now we are simplifying this equation further. We are introducing 1 over tau is equal to summation over I from I is equal to 1 to G1, and summation over J from J is equal to 1 to G2, and then we have F2J over iota Ji. Iota Ji is the same as tau Ji is the same as the tau present in the spontaneous term in equation number 3. So tau Ji is the same term, and 1 over tau ji, you know that is the spontaneous rate from the sublevel j to the sublevel I, and f2j, you see that we have already explained f2j. f2j is actually the population of the jth sublevel divided by the total population. You know that we can substitute f2j from equation number 2. So we can write f2j is equal to n2j divided by n2. So we have f2j over here, because we have introduced f2j over here, because we are going to substitute n2 from over here, that is n2j will be substituted equal to f2j into n2. So this is what we are going to substitute. That's why we have written f2j with the term, and we are going to introduce 1 over tau. 1 over tau is equal to the total rate of spontaneous emission due to all the sublevels present in level number 2 and all the sublevels present in level number 1. So this will give you the overall spontaneous rate 1 over tau, which is equal to the summation over I from I is equal to 1 to g1, and summation over j from j is equal to 1 to g2, and f2j over tau ji. And then we can introduce similarly WMLE. E stands for the emission. E as a superscript will stand for the emission in the green term, and in the blue term A stands for the absorption, as in this form. So we have WMLE, that is the transition rate from the level M to level L. M is the sub-level of level 2, L is the sub-level of level 1. So this is the transition rate from level M to level L in the emission process, that is equal to F2M into WML. And you know that F2M is what we can generally define from over here. Since we have defined F2J, so replacing J with M, the rest of the things will be the same. So it means that we have defined F2M over here, and F2M has the same meaning as F2J. So here we are in the J, we are talking about the jth sublevel of level 2, and in F2M we are talking about the mth level of level number 2. So we have F2M multiplied by WML, where ML is the transition rate from level M to L. And similarly we can replace WLMA, that is the transition rate from sub-level L to sub-level M, and A stands for the absorption. So this is the absorption rate from level L to level M. Sub-level L to sub-level M is equal to F into F of 1L multiplied by WLM. You know that FL has the same meaning as we have assigned to F1I. Here I is the sub-level of the level number 1. And here we have L is the sub-level of level number 1, and we have WLM. So we have defined these two terms, that is WLME and WLMA, by their equivalent definitions on the right hand side. So making these substitutions in equation number 3, we get dN2 over dt is equal to minus WMLE into N2. So here we have N2 over here. Because we have used the definition of 2ml over there. So you see that here we have N2, and this N2 was due to N2M replaced by N2M. Here N2M is replaced by this on the right hand side. So we can write N2M instead of J we can write M. So N2M is equal to F2M into N2. So we have replaced this quantity over here. And you know that F2M has been absorbed in the definition of ML. So WML multiplied by F2M has been written as WMLE. And similarly, we have used this definition along with the definition given over here in this equation. Instead of I, we are using L over here. So that becomes N1L is equal to F1L into N1. And this F1L has been used with this one WLM, and N1N has been replaced by WLMA. So making these substitutions over here and similarly introducing tau over there, and also using the definition given over here in this equation, N2J is equal to F2J into N2, using the definition from here and using F2J in the definition of 1 over tau over here, we can write equation number 3 as given in equation number 4. So dN over dt is equal to minus WMLE multiplied by N2 plus WLMA multiplied by N1 minus N2 over tau. That is, we have written the total, we have written this equation in terms of the total population of level 1 and level 2. So you see that on the left hand side we have the total population of level 2, which is N2, and we have N2 in the term, in the next term, and then we have N1 in the absorption term, and then we have N2 in the spontaneous rate emission term. So we have equation, we have written this equation 4 instead of equation number 4. Equation number 3 was written in terms of the sublevels, and now we have written the equation number 4 in terms of the population of the level 1 and level 2, that is the total populations, where WMLE is the effective rate of stimulated emission and WLMA is the effective rate of stimulated absorption. The change in flux dF when the beam travels a distance dz in the material is given by, so dF is equal to WMLE into N2 minus WLMA into N1 into dz. Rather than using the WML, we have used the effective rate of stimulated emission WMLE and effective rate of stimulated absorption WLMA. So we have used these terms, and then you know that the rest of the definition of the change in flux is the same as we have been using before. So dF is equal to WMLE into N2 minus WLMA into N1, and this parenthesis multiplied by dz, where dz is the distance that the light will travel through the material. So here we are just manipulating, we are doing some simple calculus, that is, we have divided all the two terms in the parenthesis by capital F, and then we have multiplied by capital F outside the parenthesis in the first term. And then in the second term we have given some color, that is WML over F represented by red and WLM over F represented in blue. And there we have represented WMLE by its full form, that is WML into F2M, and WLMA was replaced by its full form, which is WLM into F1L. And then you know that WML over F is actually the cross section or transition cross section, or you can say that it is the emission cross section, because M to L, the M is the sub-level, M to L sub-levels, where M corresponds to the upper level, upper sub-level, and L corresponds to the lower sub-level, that is the sub-level corresponds to level 1. So sigma ML is actually the transition, transmission cross-section. And then we have F2M into N2, and then we have replaced WLM over F, that is the blue term in the above parenthesis, in the above term, by sigma LM. And sigma L is again the absorption cross section, because it goes from level L to level M, and the rest of the quantities are, you see, that are the same. Then we can write this sigma ML multiplied by F2M by sigma MLE, and then we have also written sigma LMA by instead of sigma LM into F1L. So these two terms have been replaced by sigma LMA. So you see that we have now defined the change in flux when a beam of light passes through the material as dF is equal to sigma MLE into N2 minus sigma LMA into N1, and this whole parenthesis is multiplied by total flux F multiplied by the change in the multiplied by the distance dz, as shown in equation number 5. Because in writing equation number 5 we have introduced sigma MLE is equal to sigma ML into F2M and sigma LMA is equal to sigma LM into F1L. So these red terms on the left hand side, that is the cross sections, are actually the effective stimulated emission. In red is the effective stimulated emission and in blue is the absorption cross section. So we have written the effective stimulated emission and effective absorption cross sections for this case. So you see that we can write G when we have the first term greater than the second term. We can write G is equal to sigma MLE into N2 minus sigma LMA into N1. So this term G is called the gain coefficient. Similarly, if the other term is greater than the first term, we can write alpha. Alpha is equal to sigma LMA into N1 minus sigma LME into N2, which is the absorption coefficient. So sigma LMA can be determined experimentally from the absorption measurement if the material is in thermal equilibrium and exposed initially with incident beam, in which case N2 is initially 0 and N1 is equal to Nt, that is the total population is present in level 1, and alpha is equal to sigma LMA into Nt initially. Note that in case of sublevel L and sublevel M, note that in case of the sublevels L and M are non-degenerate or have the same degeneracy. If they are non-degenerate and have the same degeneracy, then we can write that sigma Lm is equal to sigma Ml. So these two sigmas will be equal to each other when there is no degeneracy, or when the levels are non-degenerate or have the same degeneracy. So you see that we have calculated the gain coefficient, we have calculated the absorption coefficients, we have calculated the gain coefficient, absorption coefficient, we have calculated the stimulated emission cross section, we have calculated the absorption cross section for the case in which the sublevels were strongly coupled. So this is the case we have addressed in this slide. So this is the end of slide number 57.